You ever look at some piece of technology, a robot arm, the cruise control in your car, and just wonder, how? How can engineers possibly predict, let alone control, something so complex? Well, it's not magic. It turns out they have a secret, a powerful shortcut that lets them model and build the world around us. And today, we're going to pull back the curtain on it.
It all comes down to this one question. Because, let's be honest, when you're trying to describe the real physical world, the problems you run into are almost always incredibly hard.
I mean, just look at this DC motor. Seems simple enough, right? But think about what's happening. You've got electricity creating magnetic fields, which makes a rotor spin, but then there's friction fighting against it, all at the same time. Trying to predict exactly how fast it'll spin with a certain amount of voltage? Yeah, that is a really, really tough problem.
Okay, so to really get why this shortcut is so brilliant, we first need to appreciate just how hard the normal way of doing things is. Let's dive into that first.
You see, the universe doesn't really speak in plain numbers. It speaks in the language of change. Think about it. The speed of a car, the flow of electricity, the temperature in a room, it's all about how things are changing from one moment to the next. The official language for that is calculus, and engineers use a specific tool called differential equations. These are basically just math sentences that describe, moment by moment, how a system is behaving. And this right here, this is the whole game. On the left, you have the time domain. That's the real world, the native language, described with those messy, hard-to-solve differential equations. But on the right, you have a completely different world, the frequency domain. And in this other world, those impossible calculus problems magically turn into simple algebra. The big question, of course, is, how do you get from one world to the other?
Well, this brings us to the absolute hero of our story, a super clever mathematical tool that lets engineers sidestep all the really hard work.
And this image explains the entire strategy perfectly. It's so elegant. Instead of trying to wrestle with the hard problem head-on, you just don't. You use a special trick to transform it into an easy problem, you solve the easy version over here, and then you just transform the easy answer back into the world you started in. Problem solved. It's a brilliant detour.
That special trick, that magic translator, has a name. It's called the Laplace Transform, and its entire job is to be our interpreter, to take the complicated language of calculus and turn it into the simple, clean, friendly language of algebra.
And here's what that actually looks like. On the left, you've got a pretty typical differential equation. It looks kind of scary, right? All those dots and weird symbols. But look what happens after you hit it with the Laplace transform. Poof, all the calculus is gone. It's just a straightforward algebraic equation. We've turned a really difficult math problem into something you basically just have to solve for x.
So we did the transform, we got our easy algebra problem, but what does that actually get us in the end? Well, it gets us the system's most important secret. It gets us something called the transfer function. The best way to think about this is like a system's unique fingerprint, or its DNA. It's a simple little fraction, the output over the input, that perfectly captures the very essence of how that system works. It's the system's blueprint.
And this simple diagram shows you how beautiful that is. You have some input, say you telling your cruise control to go 70 miles per hour. That command goes into the box, which is our transfer function. And what comes out the other side is the predicted output, the car's actual speed. It's clean, it's predictable, and it's incredibly powerful.
So this whole thing becomes a repeatable playbook for engineers. It's a 5-step process. You start with the real-world thing, use physics to write down that hard differential equation, use the Laplace transform to jump into the easy world of the frequency domain, and boom, you extract that all-powerful transfer function blueprint.
Okay, now we get to the part that I think is just completely mind-blowing, because this shortcut doesn't just work for one kind of problem. It actually reveals a deep, hidden connection in the way the world is built.
So check these two things out. On the left, you've got a block of metal on a spring with a shock absorber. Purely mechanical. On the right, you've got a simple electrical circuit with a few components. They look like they come from completely different universes, don't they?
But here's the crazy part. They are the same. The math that describes them is identical. They have the exact same transfer function blueprint. The laws of physics don't care if it's a moving block of steel or a bunch of electrons flowing through a wire. This table lays it all out. A mass, which fights against being moved, behaves exactly like an electrical inductor, which fights changes in current. A spring, which stores up energy when you stretch it, is the twin of a capacitor,
which stores up electrical energy. It's this beautiful, unifying idea that makes engineering so incredibly powerful. You solve a problem once, and you've solved it for a whole family of different systems.
All right, so let's bring this all home. Let's connect this abstract world of math back to the real-world stuff that you and I use every single day.
This whole thing isn't just a cool thought experiment. This shortcut, this jump to the frequency domain, is literally the reason we can design and build all of the amazing control systems around us. From the robotic arms in a factory, to the stability controls on an airplane, to the tiny little filters inside your phone that make sure your calls are crystal clear, it's all built on this foundation.
This quote really just sums up the entire engineering philosophy perfectly. You start with the physical world, you translate it into these powerful mathematical models, and then you use those models to analyze, predict, and ultimately design the future.
It really is a powerful idea, isn't it? That sometimes the most difficult problems don't need more brute force. They just need a clever change in perspective. And that kind of leaves you with a final thought. What other impossible problems are out there right now, just waiting for someone to find the right shortcut to make them simple?